Hello everyone, glad to meet you at lecture 6 of Automata and Formal Languages course. Today we will talk about equivalence of states of some DFA, equivalence of two or more DFAs, minimization of DFA. The question about minimization you already asked me several times, and I told you that we will study an algorithm how to build a minimal DFA equivalent to given DFA, and this is the algorithm we will study today. Okay, let's start from several questions. Given a string W and regular language L, how do I know if W belongs to L? Basically, we already did it, and we know that if L is represented by some DFA, then we have to simulate the run of A on W, and if W is in accepting state when we finish reading, then if automaton is in accepting state when we finished reading, then the word belongs to L, and if not, it doesn't belong to L. If L is represented by non-deterministic finite automaton or regular expression, so we can start first from building DFA, and then we can do the previous simulation. And once again, if reading W, we finish reading in accepting state, we know that the word belongs to the language. And if we finished reading in rejecting state, we know that the word doesn't belong to the language. Next question that can interest us, given two regular languages, is L1 equals to L2? The equality means that for all words W belongs to L1 if and only if W belongs to L2. But we can reduce this question to a little bit different problem. Are two given DFAs A and B equivalent? Actually, the problem will be the same problem. We know that A and B are equivalent if for all words W, delta cap QFS AW belongs to FA if and only if delta cap QFS BW belongs to FB. So if both the automaton belong accept the word W, or both reject the word W, and if we checked all words and we didn't find any difference, we know that automaton A is equivalent to automaton B. Let's see some examples. Here we have three deterministic finite automaton that accept language sigma star over alphabet 0, 1. The simplest and the smallest is definitely automaton B. But A does the same. In A we have two accepting states, Q0, Q1, and we actually also accept all the words. C has three states. You have to rename one of the Q1 states drawn here to Q2. So we have Q1, Q0, Q1, Q2, three states, all of them accepting state. So actually, once again, we accept sigma star. Now let's ask ourselves additional question. Given a DFA and given its 5 tuple, if we take two states P and Q, is Q equivalent to P? Or how do we know if Q is equivalent to P? If we would like to talk about state equivalence, informally, two states are equivalent if there is no string which leads from one to an accepting state and from the other to non-accepting rejecting state. The formal definition can be the following one. Two states P and Q are equivalent if and only if for all word W that belong to sigma star, delta cap QW belongs to F, and if and only if delta cap PW belongs to F. Once again, or both states accept W or both states reject W for each W in the language. So we can give a new definition of separating word. If two states P and Q are not equivalent, then there is a word W such that either delta cap QW belongs to F and delta cap PW does not belong to F, or delta cap QW does not belong to F and delta cap PW belongs to F. W is called a separating word for these two states. We can also say that P and Q are separated by W. Let's define K equivalence. In formula, two states P and Q are K equivalent if there is no word of length less than K separating between them. Formally, two states P and Q are K equivalent if and only if for all W that belong to sigma star such that length of W less equals than K, delta cap QW belongs to F in if and only if delta cap PW belongs to F. Please pay attention. I told that PVQ are K equivalent. If I will take the word with the length greater than K, the equivalence may be different. Maybe these two states won't be K equivalent. The notation for K equivalence, we write P equals, but three minus signs, index K, Q. And this is the meaning of equivalence sign. Or this is the notation for K equivalence sign. Okay, let's see the example. Here we have a 5-state automaton. Q0 is the starting state. And after 4 zeros, we reach the state Q4, an accepting state. Q0 and Q1 are two equivalent. Why? Because if I take all the word of length less equal to 2, length 0, 1, and 2, I can't separate between Q0 and Q1. Q0 on empty word stays in Q0, non-accepting state. Q1 on empty word stays in Q1, non-accepting state. On input 0, Q0 moves to Q1, non-accepting state. Q1 moves to Q2, non-accepting state. So both of them not accept 0. Let's look at the word of length 2, 0, 0. Q0 moves to Q2, non-accepting state. Q1 moves to Q3, non-accepting state. The same behavior. But Q0 and Q1 are not 3 equivalent because if I will take the word W of the length 3, 0, 0, 0, then we found a separation word. Q0, from the state Q0 with 3 zeros, we move to Q3, non-accepting state. From Q1 with 3 zeros, we move to Q4, an accepting state. Therefore, the word W with 0, 0, 0 separates between Q0 and Q1. That is why Q0 and Q1 are not 3 equivalent. Let's prove that for any K, K equivalent is an equivalent relation over Q. But first, let's remind ourselves what is equivalent relation. Let's remind ourselves equivalent relation. The relation is equivalent if it satisfies reflective, symmetric, and transitive relations. Okay, we are talking about P, K equivalent to Q. So Pk equivalent to itself. It is clear it's the same state, so we can't find the separation word. If P is K equivalent to Q, it means that Q is K equivalent to P. Once again, the symmetric relation is clear if we can't find the separation word of the length k between p and q, we can't find the word between q and p. Let's talk about transitive, and transitive relation we will prove. If p is k equivalent to q and q is k equivalent to r, that means that p is k equivalent to r. Okay, we will prove the k equivalence transitivity relation. We will assume a contrary, that p is not k equivalent to r. The meaning of not k equivalent that we found the word w with length less equal to k that is separating between p and r. Let's assume, without loss of generality, that delta cap pw belongs to f, but delta cap rw does not belong to f, and we will check delta cap qw. Okay, we have two possibilities. If delta cap qw belongs to f, there is a separating word w between q and r, in contrast to the assumption that q is k equivalent to r. If delta cap qw does not belong to f, there is a separating word w between p and q, in contrast to the assumption that p is k equivalent to q. Therefore, it must be that p is k equivalent to r. Okay, let's now talk about equivalence of states in general. Two states are equivalent if they are k equivalent for all k. Proof: there is no separating word of any length between those states. And when we would like to use the notation about equivalence notation, we just write p equivalent to q without any letter k as index. Let's see an example. Q0 and Q2 have the same behavior. They're equivalent. Why? Q0 and Q2, for each letter of the alphabet, go to the same state. With 1, they go to Q3. With 0, they go to Q1. It implies that the words of length greater than 1 won't separate them either. Why? Because with the first letter we will go to the same state, and then for the rest of the letters we will continue. Therefore, Q0 is equivalent to Q2. But Q0, for example, is not equivalent to Q1. For example, Q0 with 1 moves to Q3 in accepting state, and Q1 with 1 stays in Q1 rejecting state. Therefore, we found a separation word of the length 1. Q3 and Q1 is also not equivalent since we have an empty word. Q3 accepts an empty word, and Q1 rejects an empty word. Finding equivalent states in general. Given Q, the set of all states of the automaton, the set of all states can be divided into equivalent classes of order k. Each two states in the same equivalence class of the order k are k equivalent. If the states are an equivalence class, are equivalent for all k, then those states are equivalent in general. So basically, we will try to find equivalent classes at the automaton. At step k, we will separate our Q into equivalent classes AK, C1, C2 till Cm, satisfying K equivalence. In this process, we will use dynamic programming, where at each step, the length of the potential separating word is increases. We will add additional letter and we will look or use longer words. At step K, the equivalence classes of order K are used to calculate the new equivalence classes of order K plus 1. At each step, equivalent classes may split, but they can't merge together. Some classes or some states that were separated will stay forever separated. Okay, so let's see the basic idea in general. Let's assume that we are running equivalence algorithm as Q is separated into several classes. Let's take two states P and Q belonging to the same class Ci and satisfying the condition that P is K equivalent to Q. For PQ belonging to Ci, let's assume if there is a single letter sigma that belongs to sigma, such that delta P sigma not K equivalent to delta Q sigma, that means that we are moving to different classes, then P and Q are not K plus K plus 1 equivalent, and they should be splitted. Why? Let's think it over. If for the first letter we already moved to separate classes, why those classes were separated? Because they had some separation word. So sigma with the addition of this separation word, the meaning is that for for the word sigma w, in one case we will accept the word, in other case we will reject or get at least two different class. Okay, let's define the theorem. Let two states P and Q belonging to Q be K equivalent. The states are also K plus 1 equivalent if and only if for all letter sigma in sigma, delta P sigma K equivalent to delta Q sigma. In other words, if P K equivalent to Q and for all letters of the alphabet delta P sigma K equivalent to delta Q sigma, then P is K plus 1 equivalent to Q. If P is K equivalent to Q, but exists a letter sigma for which delta P sigma not K equivalent to delta Q sigma, then P and Q are not K plus 1 equivalent. So the question until when we continue with the algorithm, when to stop. So the theorem is if EK equals to K plus 1, then EK plus 1 will be equal to EK plus 2. And the states in each equivalence class are mutually equivalent. And we will give the proof to this theorem in a moment. Okay, let's assume the contrary. Let's assume that EK plus 1 not equivalent to EK plus 2. This means that we have two states, P and Q, such that P and Q are K plus 1 equivalent, but not K plus 2 equivalent. But this means that we have a separating word of the length K plus 2 between P and Q2. And let's define the separating word to be sigma 1, sigma 2, sigma 3, sigma K plus 2. Let's move from P on the first letter sigma 1 to some state R. And let's move from Q on the first letter sigma 1 to some state S. It is clear that R is not K plus 1 equivalent to S. There is a separating word W tag of the suffix sigma 2, sigma 3, sigma K plus 2, and W cap length is K plus 1. But R was K equivalent to S, because P was K plus equivalent to Q. If they won't be K equivalent, then P can't be K plus 1 equivalent to Q. Thus, R is K equivalent to S, and R is not K plus equivalent to S. This contradicts the assumption that EK equals EK plus 1, since we found two states that are K equivalent and two states that are not K plus 1 equivalent. That means that we contradict the assumption that EK was equal to EK plus 1. Thus, it must be true that EK plus 1 equals to EK plus 2. Please pay attention that we had to prove that EK equals, that from EK equals to EK plus 1 follows that EK plus 1 equals EK plus 2. Instead, we prove that not EK plus 1 equals to EK plus 2. Therefore, not EK equals to EK plus 1. That's what we did in our proof. But the meaning of this theorem, or the conclusion of this theorem, first time when you compute equivalence classes and you have the same set of classes, you can stop. That means that nothing else can be separated. That's it. You finish, you have all the states at the correct equivalence class. Okay, let's define an algorithm how we compute or find equivalence class of DFA. We are given some DFA A with a set Q, and we would like to find the equivalence classes over Q. Okay, we start from the step 1. We divide Q to two classes, accepting and non-accepting state, with the empty word as a separation word. So we have class C1 of the accepting state and class C2 of the rejecting state. We continue with the algorithm. While in previous step K, EK has been changed, do the following procedures at step K plus 1. For each K equivalence class Cj in Ek, for each pair of states P and Q in Cj, for each input letter sigma, check if P sigma not K equivalent to delta Q sigma, then divide Cj, or then divide P in Q to different classes. So then we divide Cj to at least two classes where P moves to one class and Q moves to a different class. Let's construct an equivalent state for a given DFA. I advise you to stop the recording and to try to solve this question by yourself. Okay, we will start with E0, empty word as a separation word. We have Q0, Q3, and we have Q1, Q2. So we have two classes. Okay, now we will move to the next step, and we will look at the word of the length 1, at the letters of the alphabet, and we will check each two states in each class. Can we separate the states with an input 0 or 1 in this case? Okay, let's look at Q0, Q3, the red color here. Q0 on 0 moves to Q1, Q3 moves to the same state. Q0 on 1 moves to the Q2. Q0 on Q3 on 1 moves to Q1, but Q1 and Q2 are the same class. So we didn't find any separation word now. So Q0 and Q3 should stay together. Let's try to separate Q1 and Q2. Maybe we can manage. Q1 and Q2 on 0 move to Q0. Q1 and Q2 on 1 move to Q3. It's actually the same state. So we know that we can't separate Q1 and Q2. Therefore, we have E1 equals to E0, and we stop. The classes that we have are the minimal number of classes. We can't divide it anymore. We can't split it anymore. Once again, additional example. I advise you to try to do it by yourself. We are given 5-state automaton, and we will separate the state with an empty word to the class with Q4 state, an accepting state, and Q0, Q1, Q2, Q3 as a rejecting state. Now we will look at one equivalence, and we can see that from Q3 and B we can move to Q4, an accepting state. For the rest of the states, Q0, Q1, Q2, we can't do the same. We stay at the rejecting state. So we are moving to our transition function, and we see that the only state that behaves differently at the group Q0, Q1, Q2, Q3 is Q3. On input B, it moves to Q4, different class, an accepting class. For the word W that equals to A, all the states go to the same class in E0. For the word W that equals B, Q3 goes to the other class. That's why we can now separate Q3. And now E1 equals to set with Q4, set with the state Q3, set with the states Q0, Q1, Q2. Okay, we can't split Q4, we can't split Q3, but we can check what can we do with Q0, Q1, Q2. Maybe we still can separate them. So we move to the next stage of the algorithm, and we would like to find the states that are two equivalent. The only class that interests us is Q0, Q1, Q2. And we can see that in Q0, Q1, Q2, Q1 and Q2 have the same behavior and Q0 has different behavior. Q0 on A stays in Q2. Q0 on B stays at the same equivalence class, Q1. Q1 and Q2 on A move to Q3, move to different class. Therefore, Q1 and Q2 behaves the same, and Q0 behaves differently. Therefore, in E2, Q0 will be a separate class. So we still have Q1 and Q2 together. Maybe we can also separate them. But after checking the automaton, we can see that Q1 and Q2 are three equivalent. Because on the input A, they lead us to the same state, Q3, and on the input letter B, they lead us to Q1, Q2, which are actually the same class. Therefore, we didn't manage to find a word that can be a separated word of the length 3, and therefore we have E3 that equals to E2, and our algorithm stops. We can't add any additional classes if we will continue with this algorithm. Example 3 will be our task for practice exercise. We will construct equivalent classes for this DFA. Okay, given two states, P and Q of the automaton A, how do we know that P is equivalent to Q? One of the possible solutions can be that we run an equivalence class algorithm on automaton A and check whether P and Q are in the same class. If P and Q are in the same class, then they are equivalent. Given two DFAs and A and B, how would decide if A is equivalent to B? If one DFA is equivalent to another DFA? The answer will be the following one. We can consider the union of the automata. We build a union automaton and we check whether Q0A and Q0B are equivalent. If the answer is yes, then automaton A and automaton B accept the same language, and that means that they are equivalent. Let's see an example. We have here two DFAs, and the question are the two DFAs equivalent? Let's build in our mind the union automaton, and we know that with an empty word, we can separate the states A, C, D to one class and B and E to the other class. Now let's see if we can divide ACD or BE to different subclasses. ACD on input A remain in the red group, A and D. ACD on input B move to the violet group. So it's the same behavior. Let's try to separate B and D. Maybe we can manage to do something different. B on input 0 moves to A. Input on E on input 0 moves to C. The same red class, accepting state. B and E on 1 stay in B or E. The same rejecting state. So we can't continue with the separation of the classes. Since E0 equals to E1, we finished. We can't split any more classes. We have the starting state of the first automaton A in the same equivalence state as the starting state of the second automaton D, and therefore the two DFAs are equivalent, and that means that they accept the same language. Okay, now let's talk about minimization problem. The problem that already several students asked. How do we know that the solution we built is the minimal one? And I told, listen, you have to try, but later during the course, we will study minimalization algorithm. So given a DFA, we can find a given a DFA A, we can find a DFA B such that the language of A equals to the language of B, and B has a minimal number of states among all DFAs accepting the language. This automaton have a special name, minimal DFA. And to build a minimum DFA, we have a well-defined algorithm. Let's try to think what is the meaning that automaton is not minimal. The automaton is not minimal. That means that we have two states that actually behave the same, and they can be united. Two states that can be united actually are equivalent states. So basically, we will run the equivalence algorithm that we used before and unified all the states in the equivalence class. We will draw them as a single state, and the resulting automaton will be a minimal DFA. Okay, so we are given some deterministic finite automaton A, and we would like to build a smaller DFA B. First of all, we will start with elimination of all states that cannot be reached from Q0. Then we will use an equivalence algorithm that we started before. And let QB be the resulting set of equivalent classes. The starting state of Q0B is the class that has Q0A in it. The accepting states FB will be the classes including accepting states from FA. Transition function of B for each state P in QB and letters sigma in sigma, delta B P sigma equals R. The meaning of R, we will take all state Q in P. And we will see where we go with the letter sigma. And then we will unite the results and we will have the state R. Okay, I advise you to build a minimal DFA for this automaton. We already applied the equivalence algorithm, and we know that Q0 equals to Q1, and we should draw Q0, Q3 as a one state, and Q1, Q2 as an other state. Q0, Q3 will be an accepting state, Q1, Q2 will be a rejecting state. Q0, Q3 will be the starting state since we have Q0 in it, and the resulting minimal DFA will look like this. So we have only two states, Q0, Q3, and Q1, Q2, and the language of this automaton is the language that accepts all words over alphabet 0, 1 with even length. Additional example, once again, I encourage you to solve it by yourself. We are asked to construct a minimal DFA equivalent to a given DFA. We already used equivalence algorithm and we computed E3, and we have three groups, Q1, Q2, Q0, Q3, Q4. So these four groups, we have Q1 and Q2 as the same state. So we will draw Q1, Q2 as the same state. Q0 will be the starting state of the new automaton. Q4 will be an accepting state. Q1 and Q2 will be drawn together. And the transition function is actually written here. So we just have to move to the correct state. This automaton is a minimal automaton equivalent to the previous DFA that we had. We almost finish. Given a DFA whose minimal DFA is M, can we find even smaller DFA N such that Lm equals to Ln? Basically, no. The minimal DFA that we constructed for A is a DFA that has a few states of any DFAs equivalent to A. So we can't have another even smaller DFA. The proof is not given here during the lecture, but it can be found in the slides of this lecture. So the meaning of the previous sentence, the previous theorem, is that every regular language has a single minimal automaton. And if we found theoretically two different automatons, it's actually isomorphism. It's the same graph. We just named the states probably different or drawn states in a little bit different form. So once again, the proof to this theorem can be found at the lecture slides. Okay, that's it. We reach the end of Unit 5. We talk about equivalence of states, equivalence of DFA, and minimal DFA. That's it for this week. Thank you. See you during a Zoom meeting.